All right, so assignment number 2, applications of Newton's second law. This is really just more practice. This was meant to be more or less independent, but I wanted to give you a walkthrough for those of you who weren't here today, just so you kind of had a little bit of a helping hand, given all the confusion with making new calendars for us going remote and everything. Again, I'll extend this one by a day. So don't fret if you wanted to look this over a little bit more before submitting it, or even just resubmit the assignment after I've already graded it. That's perfectly fine. This is just meant to be kind of like a helpful review recap for you guys. Some of these things are actually at the very beginning old stuff that we haven't talked about for a minute that I wanted to bring back. Like number 1, this was actually a concept, an idea from our Unit 1 chapter. This is a vocab term from there that we used in Unit 4 when we took our velocity vectors and broke them up into our y directions and our x directions, and you had that cannonball that was firing the cannon, or the trebuchet, or someone kicking a soccer ball at an angle, whatever it might have been. This we've already done, and what I refer to this as, I use the word every now and then when I ask you to do this sort of problem, is vector resolution. I'll write that down real quick. Vector resolution. So to resolve that vector literally just means to break it up into its x and y components, and that's all that needs to be. We've done that with velocities. We'll do that again with forces here in this unit. The answer to number 2 very clearly is volume. Why would I bring that up? Mass, volume, and weight are 3 things that society tends to get they have misconceptions about. Oftentimes they'll actually compare them interchangeably or use them interchangeably, and they really shouldn't at all. The amount of space an object occupies is its volume. The amount of material that is present, is going to be your mass. And last year in chemistry, you guys talked about this in terms of density, right? You've got a quantity of stuff that is there, and then the amount of space that it occupies. And if you've got a lot of stuff in a small space, you have a very dense object. If you have very little stuff in a large space, you have a very low density object, and that was really all density was getting at. But that's mass and volume, 2 very different fundamental measurements, just like weight is also a fundamental different measurement. Weight is the force, and this is the second time I've written this for you guys, of gravity acting on mass. Right? So the force of gravity, if you go far enough away from the Earth, it will effectively reach 0, right? If you leave the Earth's ability to interact with you gravitationally, get far enough away, then you essentially become weightless. We'll talk about that vocab term in a little bit, but you essentially become without weight, but you still have mass. You still have all of your cells. You still have all of your subatomic particles that make up those cells. Everything is still there. The only thing that changed is the absence of gravity, and that was all. Number 3, we come back to this idea of directly proportional, inversely proportional, or these are our graphs from Unit 1, or that quadratic graph, right, that we talked about, the parabola. Directly proportional meant that as force increases, or as, let me rephrase this to make more sense. Technically, yes, that would be true, but it's weird to say. As mass increases, the force required to remove that object also increases. Right? Think about it this way. If you're walking around on Halloween, pulling your younger siblings or cousins or whomever in a wagon behind you going house to house, if there's only one kid in the back of the wagon, you don't need a whole lot of force to pull it. It's pretty straightforward. It's pretty easy. But if all of their friends also pile in the wagon and now there's a lot more mass, you have to pull a lot harder in order to get that wagon to move, right? Replace that with, I don't know, a car that gets stranded on the side of the road. Even more mass requires even more force to get moving, and that's what directly proportional represents. It's the idea that if one variable increases, so too will the other. That's the exact opposite of something you're going to see on the back side of this worksheet, or was it on the front? It doesn't matter. And that is, it's on assignment 3. Inversely proportional. Inversely proportional is the exact opposite. That is like mass and acceleration, right? Mass and acceleration are what we would call inversely proportional, and it's the exact opposite of what was there before. If mass increases, then your acceleration decreases, right? If you've got more kids in that wagon, you can't accelerate it as quickly as you could have before. If you get stuck behind a full semi-truck at a red light, that's going to suck because it's going to take them forever to accelerate to the speed limit, whereas if you're stuck behind a motorcycle at a red light, barring some really, really, really slow individual riding that bike, right, it's probably going to accelerate a lot quicker than that semi-truck or a lot faster than that school bus. So the more mass you have, the slower you accelerate. That's what inversely proportional relationship would be. So 2 examples of just this unit, right? Force and mass, directly proportional. Mass and acceleration, inversely proportional. Number 4, we already talked about. It's opposite. All right, that was from the last page. And then number 5. This was the last one I wanted to do with you guys for the most part until we get to the back. You've got the weight of the object, which is a force of gravity. So I'm going to start writing out F equals ma. I just changed the a to be gravity because I wanted to be specific as to where the source of this acceleration was coming from. And again, just like I mentioned in the last video, this is relatively straightforward with the exception of the part that's going to look weird to us because it's never what we see on a scale, and that's totally fine. Weight is a force. Forces are vectors. Your weight for this object is negative 100 newtons. If you put it on a scale, the scale would push up with a force of 100 newtons, and that's the force it would report to you because it's positive, right? And that was really all it was going to be. Number 9, watch out for this, right? One of these is not like the other. Kilograms is correct, grams is not. Make sure you convert that. And then the only other thing that I wanted to mention here was number 14, because it gets you started with 15, 16, and 17. These are your elevator problems. And the idea behind how your weight might appear to change, even though your weight really doesn't, how your weight might appear to change in that elevator as it is going up or coming back down is going to be because you've got multiple sources of acceleration acting on you. You have the acceleration from the elevator, yes, but then you also have the acceleration due to gravity. You have the acceleration of the elevator, and you also have the acceleration due to gravity. There's an interplay. There's an exchange there. If it's rising, they're either going to work together or against one another. If it's descending, it's either going to work together or work against one another, right? Now, had this been a class where we would have had a lot more time to work on this, or maybe just even honors, I would have drilled this part into you, why they work together in one scenario versus why they don't in another. But you can just bypass that and think about what it really feels like in real life when you're in an elevator. When you begin going up in the elevator, everything starts to get a little bit heavier, right? And so shoulders drop down, knees might bend a little bit, backpacks feel heavier for a moment. Just in that first fraction of a second, you begin accelerating upward. And because of that, then you've got your 2 accelerations working together. So if you look at the front of the packet, I have written this for you. It's basically shorthand for the force you would experience if you were looking at a scale so that you could measure your apparent weight on an elevator as you go up. Right? I tried to make it real easy. This is the 3rd bullet point for you guys. I'll even write that here. It's your 3rd bullet point number 3. And it's written out exactly as F equals ma always has been. It's your force is equal to mass multiplied by whatever weird thing is happening to your acceleration right now. And in this particular case, your acceleration and gravity have this particular relationship. Again, I'll draw it out for you guys if you really want to see it when we meet again. But most students just kind of take the equation and run with it, which is totally fine with me. You know, for how in-depth we're going to take this, that's fine. Take the equation, run with it. As long as you know if it's going up, use the one with the up arrow, and you're set. This is 85 kilograms as your mass, multiplied by -10, because that was your acceleration due to gravity, minus 1.5. Notice the way that I set this up here, the acceleration actually gets larger. It gets more negative. And that's going to result in your force, your weight, feeling a little bit more than it should have. Now again, this is only going to happen and be the case for the first fraction of a second as the elevator is accelerating upwards. Once it's moving at the rate it needs to move, it's going to stop accelerating. It's just going to start moving at the same rate. And so there isn't that additional source of acceleration, and your equation goes right back to just being F equals mg, because there is no additional acceleration from the elevator that you've got to do something weird with gravity. And then number 16 is the exact opposite, right? On your scale, as you're going down, you're going to notice that equation changes because gravity and the elevator's acceleration aren't working together. You're going to feel a little bit lighter. Right? Maybe you get those butterflies in your stomach or whatever it might be. But that was your quick overview of what I did in class to help students with assignment 2. This one, number 13, I encourage you, if you're stuck on it, go back and check out the Unit 1 video when we talked about number 5, because that one's really, really, really similar. Both of those are good. Good problems. I like them. I'm going to use them later.